This is the last lecture of carboxylic acid derivatives, and we're going to look at nitriles from section 18 and 19 of chapter 20. Nitriles look very different from the rest of the carboxylic acid derivatives because they lack the carbonyl group. They don't have that oxygen present. They're still considered carboxylic acid derivative because you can hydrolyze them in the presence of an acid or a base to get carboxylic acids. The stability of nitriles is a little difficult to explain using the same resonance structure approach that I've tried with the rest of the carboxylic acid derivatives, but it's enough to say that the carbon in the nitrile carries a small positive charge because nitrogen is less electronegative and is less able to pull electron density off of that carbon than in the carbon of a carbonyl group. The nomenclature of nitriles also helps us see them as carboxylic acid derivatives because it's based on carboxylic acids that the nitriles could be hydrolyzed to make. So for example, if you consider this very simple compound right here where you have a nitrile attached to a methyl group, we need to see that as a carboxylic acid connected to a methyl group. And if it were, this would be ethanoic or acetic acid. When it's a nitrile, they give it two names, and the two names differ by a letter. So the two names for this compound could be, if we call this acetic acid, it would become acetonitrile. But if you refer to it as a systematic name by its alkane, so this is a two-carbon group, so this is ethane, then you can either call it ethane O-nitrile or ethane with an E-nitrile. Okay? So here's the ethane with an E-nitrile. Here I'm showing you the common name, acetonitrile, but the correct name for this could also be ethanonitrile. So when there's not common names present, like the aceto group or the benzoic acid group that we're going to see right here, then you can correctly name these either as the alkane with an E-nitrile or the alkane with an O-nitrile. And we'll see that right here. It's kind of a weird system. I don't know why we've kept both systems of nomenclature when it's just an issue of almost throwing a random vowel in there. So this is a 1, 2, 3, 4 carbon group. As a carboxylic acid, this would be butanoic acid. So as a nitrile, we refer to it as butanonitrile with an O or butane nitrile with an E. Both are correct and are different. I haven't yet specified the methyl group. The methyl group would be at the 2 position because the nitrile dictates the number 1 position. So this would be 2-methyl-butane nitrile or 2-methyl-butanonitrile. There's not one that's functional class and substitutive class, or at least that's not how I understand it to be. Sometimes you put an E in there and sometimes you put an O in there. This right here is kind of a weird compound. It is derived from benzoic acid, so the easiest name is to call it benzonitrile. If you have a 1-carbon carboxylic acid derivative hanging off of a ring system, then it is also correct to name it by stating the name of the ring benzene, and then stating the name of the carboxylic acid group as carbo. So it ends up being, it should be a phenyl group when it's a substituent, phenyl carbonitrile, or you can call it benzonitrile based on benzoic acid. These probably aren't the best examples for nomenclature that I could have chosen, and the one that we're going to see most commonly with nitriles is based on this structure over here, where you just name it as an alkane group, and then you feed that alkane group into the word nitrile using an E or an O. Over here, I'm dealing with some common names I'm trying to show you simultaneously. But this right here is the best example for how we want to think about the nomenclature of nitriles. So let's name some of these. We're going to jump right into increased complexity with the nomenclature because now we have multiple functional groups. And the purpose of this is to remind us of the priorities of the different functional groups. So this is a ketone and this is a nitrile. A nitrile is a carboxylic acid derivative. All the carboxylic acid derivatives have priority over aldehydes and ketones. So this is a 4-carbon, 1, 2, 3, 4 carbons there that extend out from my carboxylic acid derivative, highest priority substituent. So this is butane nitrile or butanonitrile. At the 1, 2,3 position is an oxo group, so the correct name for this is 3-oxobutane nitrile. If you have multiple carboxylic acid substituents in your parent chain, then you have to remember which of those carboxylic acid substituents carries the highest priority. Carboxylic acid itself is the highest priority of the carboxylic acid derivatives, and so this is going to be some type of 1, 2, and that's it. So this is a 2-carbon carboxylic acid, and I did not count this carbon right here. And this is something that's kind of unique to nitrile-containing compounds. As a substituent, you need to consider both the nitrogen and carbon belonging to the substituent. So we don't actually count the longest continuous stretch of carbons. We count only the 2 carbons that are not part of this nitrile. When nitrile is not the parent chain, but rather a substituent, it's referred to as a cyano group. So this is a cyanoethanoic acid, where the cyano is attached at the 2 carbon of the ethanoic acid. We can also call it acetic acid, so you could call this cyanoacetic acid. Again, it's correct either to call it 2-cyanoacetic acid or 2-cyanoethanoic acid. Here's another case where we have a nitrile at the 2 position of what could be an acetic acid, but it's not. It's an acetyl chloride. And this requires us to remember the priorities of the different carboxylic acid derivatives. And the carboxylic acid derivatives, the ones that are an oxygen-containing carboxylic acid derivatives, such as carboxylic acids and esters and anhydrides, have higher priority than the halogen-containing carboxylic acid derivatives, which have higher priority than the nitrogen-containing carboxylic acid derivatives. So here the halogen has a higher priority than the nitrogen-containing carboxylic acid derivative, and therefore this is based on acetic acid, so it's acetyl chloride would be the parent chain right here with the cyano group at the 2 position. Our last nomenclature requires us to consider the priority of something that is a carboxylic acid derivative versus the priority of something that is a carboxylic acid derivative. Both of these carboxylic acid derivatives contain nitrogens, and so now we have to split hairs. Which of the nitrogen-containing carboxylic acid derivatives has higher priority? And the answer is amides take priority over the nitriles. So this is a 2-carbon parent chain, and if this were a carboxylic acid, we'd again refer to this as acetic acid or ethanoic acid. When the parent chain is an amide, then we get rid of the oic acid and replace it with amide. So this is acetamide, or ethanamide would be the parent chain name, with the cyano group at the 2 position. So 2-cyanoacetamide or 2-cyanoethanamide. If you're still not quite clear on the priorities order of the different carboxylic acid derivatives, then I'd encourage you to go back and review the priorities that I showed you in the previous lecture. The chemistry of nitriles has, we've seen 3 different reactions involving nitriles. The first one was way back in an earlier chapter in the first semester course, and this was the cyanide as a nucleophile displacing halogens. This is a good nucleophile and a weak base, so it works usually with primary or secondary alkyl halides to produce nitriles. We also looked at the reaction of aldehydes and ketones with usually a base catalyzed reaction, so not hydrogen cyanide, but rather cyanide itself to produce cyanohydrins. We then taught, and this isn't showing up on this slide, but then we talked about how we can take cyanides and hydrolyze them to carboxylic acids. And when I showed you that, I said we'll talk about the mechanism later. And that later is today, because all of the carboxylic acid derivatives can be hydrolyzed to a carboxylic acid. The last reaction that is completely new to us is the conversion of an amide to a nitrile. Energetically, nitriles are downhill from amides, so if we can pull water off of an amide, we should be able to go downhill to produce the nitrile. So there's technically 5 different reactions buried within this slide. One is the substitution reaction that we saw in the first half of organic chemistry, then the formation of the cyanohydrins when we react cyanide with aldehydes and ketones. Also is the acid and base catalyzed hydrolysis of nitriles to produce carboxylic acids, which isn't explicitly shown on this slide, but hopefully you recognize that is a feature of every single carboxylic acid derivative, that you need to know the mechanism for the acid and base catalyzed hydrolysis of those different carboxylic acid derivatives to form carboxylic acids. And finally, the dehydration of amides to give us nitriles. The dehydration of amides to give nitriles is accomplished using phosphorus pentoxide. And the nomenclature of phosphorus pentoxide is incorrect. It's the name that we commonly use, phosphorus pentoxide, but the actual chemical is most likely P4O10, which would be tetraphosphorus decoxide, but can also be represented as P2O5, which would be diphosphorus pentoxide, and then we say it as phosphorus pentoxide. So at this point, we're just giving up on any nomenclature rules, and this is just because historically they gave up a long time ago and nobody called them on it. So now we're stuck with this name that doesn't make any real chemical sense other than the fact that it contains phosphorus and oxygen. As we saw with the Wittig reaction, in the Wittig reaction, a phosphorus cleans an oxygen off of aldehydes or ketones. It was the one with the phosphorus ylide where it ends up pulling off the oxygen and replace it with an alkene. Here, we're going to take, so I have a rather complicated molecule here that I pulled from the literature, and what you see is an amide, and then the rest of the molecule is really not important in this chemical reaction. And the amide has the carbon and the nitrogen. We're reacting it with phosphorus pentoxide, and we end up with the cyano group right there when we're done. This reaction evidently requires heat as the main reactant, and they said no solvent. And so I'm not exactly sure if they just ground these powders together, because I don't think any of them are liquids at room temperature. So not sure exactly what they did here. The mechanism for the reaction of the dehydration of amides to form nitriles using phosphorus pentoxide is actually kind of a mess. So instead, I'm going to use this reagent right here, POCl3. And this is kind of like the difference between using an acyl chloride and a carboxylic acid to do Fischer esterifications, or chromic acid versus PCC. And this is done under base conditions. Unfortunately, this is not a nucleophilic acyl substitution or a SNAC mechanism. It has some features that look SNAC-ish, but it is kind of a unique and different type of mechanism. In the first step of the reaction, and I'm going to fix this here in just a second and get rid of that resonance arrow and replace it with the real arrow. The first step of the reaction, the amide unloads its electron density through the oxygen to push into the phosphorus. This definitely looks like step 2 of SNAC, where a nucleophile pushes into a carbonyl and breaks the pi bond out onto the oxygen. The reaction is base catalyzed because of the presence of pyridine, so the presence of this oxide ion here is not a big deal. Like the SNAC mechanism, the third step, so remember the first step would always be the preprotonation of the oxygen, but the solution is basic, so we skip that first step. The second step of the SNAC mechanism is something pushing into your carbonyl carbon. In this case, we're pushing it into the phosphorus. The third step is a deprotonation of your incoming nucleophile if it carries a positive charge, which is exactly what we're doing. The fourth step is the protonation of a leaving group if it needs to be protonated. Chlorides don't need to be protonated, so we cut to step 5 in this SNAC variation, and the electrons swing down, reform the phosphorus-oxygen double bond, and eject the chloride. If this were the SNAC mechanism, well, that would be a carbon right there, not a phosphorus, and at this point we would be done. So this is why this is kind of like a SNAC, but different. And what happens in the last step is that the nitrogen drops the electrons down to make a triple bond, pushes off the phosphorus, and then there's a final deprotonation step. You'll notice that I said that this was a base catalyzed reaction. And how is it catalyzed then? Because we have two pyridines that are being consumed in the reaction. And the answer is that this chloride ion will eventually pluck a hydrogen back off of one of the pyridine conjugate acids called pyridinium. And then this compound right here ends up carrying a negative charge, and it could potentially pull a hydrogen off of the other pyridinium to regenerate your catalytic base. We don't show those steps because they're inorganic, and this mechanism is really different. I hope you can see some similarities to SNAC that will help you kind of recognize it as SNAC-ish. But this last step here, where you end up driving off the oxygen, is really not like much else that we've seen in the past. And so this is called a dehydration of an amide to form a nitrile, and you need to take the time to memorize this mechanism. I did fix that resonance, the resonance arrow, and just made it a directional arrow. So in case you were worried, now it's fixed. Let's take a look now at spectroscopy of nitriles. They are a carboxylic acid derivative, but because they don't have the carbonyl carbon or oxygen, then the spectroscopy looks a lot different. So here's a summary statement of the spectroscopy, but let's instead jump to actual examples. So here's propionitrile. This is based on propionic acid, so it is a 1, 2, 3 carbon nitrile with the triple bond nitrogen. I showed this before, but when you go to the database for C13NMR, a lot of times instead of drawing out the carbon, they'll just identify it by number, and then they give you a table that tells you that carbon number 3, right there, has an integration value of 120.97. Carbon number 2 is all the way down here at 10.93, and carbon 1 is at 10.60. Notice how very close those two carbons are to each other. And if we were looking at a C13NMR, we'd have to point out that those are actually two different peaks. A couple of things to note about the C13NMR. This is a carboxylic acid derivative, and in the past, all of the carbons in the carboxylic acid derivatives have shown up at about 170. Nitriles don't. They show up at about 120. The other thing is, because the nitrogen doesn't really pull off that much electron density, this pi bond right here, in fact the combination of pi bonds, ends up being a very electron-rich group. And so the neighboring methylene carbon actually has a shift value that's down below 20. And this violates the rule that I've used in the past, where I told you that if anything is below 20, it's definitely a methyl group, unless it's not. And this is the case where it's not. That the nitrile tends to produce very low shift values for carbons that are associated with the nitrile, even if they're not necessarily methyl groups. The proton NMR is kind of inconsequential because the nitrile group itself doesn't have any room for hydrogens. And so this is just carbon 1 and 2 are just an ethyl group, and we see the standard quartet triplet that you expect to find with most ethyl groups. The shift values here are relatively similar to any other alkyl group that you'd see. And so if you just had an ethyl group hanging off of anything, you'd kind of expect to see this right here. There's nothing about the nitrile that really allows us to see anything useful in the proton NMR. Your mass spec. This is a nitrogen-containing compound, so we should see an odd value on our molar mass. The molecular ion peak here is at 55, which doesn't really look like the molecular ion peak because of how small it is. The M-1 peak is huge. So that could be very confusing. Let's go back and look here at the note. This is what's going on there. When you have a nitrile, the lone pair on the nitrogen is the electron that gets knocked off in the ionization chamber of the mass spec. And the solution to the stability problem is usually for not the carbon that's connected to the nitrogen, but the alpha carbon over here tends to lose a bond in order to produce this back-to-back double bond right here. And this happens so readily that the M-1 peak becomes a very significant peak in your spectrum. So here is the molecular ion peak, there's my M+1 peak, and this M-1 peak is a good indication that you're looking at a nitrile group, because nitriles tend to produce substantial M-1 peaks. Now that only occurs if the carbon immediately adjacent to the nitrile actually has a hydrogen that it can lose. The IR is actually the most interesting thing in nitriles because the carbon-nitrogen triple bond shows up at 22 or about 2250 in this particular diagram. And this is nothing else we've seen actually shows up in this region that makes a peak this tall. Carbon-carbon triple bonds actually show up right around 2200, but they tend to be very short. So carbon-nitrogen triple bonds make a very significant peak at 2200. And it doesn't look like a carbonyl peak because it's very thin. Carbonyl peaks tend to widen out. This right here is actually what we expect to see with amides. So this is another case where probably during the course of the infrared experiment, some background hydrolysis is converting your nitrile group into an amide, which is what happens during the hydrolysis of nitriles. So this is represents contamination or decomposition of your compound. But the peaks that really matter here are you have this nitrile peak at 2200. Here's a practice problem where we can consider both the chemistry and the spectroscopy of nitrile-containing compounds. I would encourage you to pause the video and see if you can determine what the product of this reaction is, and then more importantly, assign carbons from the C13 NMR and match them up with the carbons in the product. Let's talk about the correct answer. This cyanide right here is the active reagent. It's a nucleophile, and it's going to come over here and start attacking electrophilic positions. Now, it's a fair question to ask which of the two electrophilic positions it's going to attack, whether it's going to come into this position or plug into the aldehyde, and the answer is it's going to attack both. I know that because my compound right here has 1, 2, 3, 4 carbons, and my C13 NMR of my product actually has 6 peaks. That means that during the course of the chemical reaction, I'm going to add 2 new carbons to the compound. And so what I'm going to do is going to add cyanide as a nucleophile to bump off the bromide. So we're going to have one cyanide that's clinging to the end of the compound where the bromide used to be. And then we're going to come to carbon 4, carbon 3, carbon 2. The carbonyl carbon is going to be converted into a cyanohydrin. So this should be the structure of the compound. So what are the ethanol and the water doing? Well, they're serving as sources of hydrogens to make the cyanohydrin, and they're also there for solubility issues. This is not likely to be soluble in water, but it is likely to be soluble in ethanol. And so we can often use an alcohol-water mixture as our solvent system. We usually don't like to do that in an SN2 reaction, which is exactly what's happening here at carbon number 4, but evidently it worked. I think I pulled this one from the literature, or I just made it up. I'm pretty sure I pulled this one from the literature or from your textbook. So anyway, here's the product. Of the carbons now, my C13 NMR, I have, let's go back to the original numbering system, not because it's the correct numbering system, but just so that we can give these carbons identities. So we're going to call this carbon that used to be the carbonyl carbon number 1, number 2. Actually, I'm not. I don't want to use the number 1 and 2 because that might be confusing when we think about nomenclature. So instead, I'm just going to refer to them as A, B, C, D. And then we'll call these two E1, and this one will be E2. Why not E and F? Well, they're both nitriles, so I want to try to use, I don't know, E1 and E2. All right, so notice how carbons B, C, and D are all right here methylene carbons. So they're definitely going to show up down here in this region. Carbon A is bound to a single bond oxygen. So whenever you see single bond oxygens, we expect those to occur between about 55 and 80. Epoxides were showing up as low as 40, but this one right here, this is definitely carbon A. And then E1 and E2 both are going to show up at 120. That is in a C13 NMR where we expect the nitriles to show up. So you can refer to these either as nitriles or cyano groups. Either one is correct. E2 is probably going to have a higher shift value because it's adjacent. It's not adjacent, but it's closer to this alcohol. So I'm going to put E2 over here on the left-hand side. and I'll put E1 here on the right-hand side. I'm actually surprised at how close these are to each other, and there might actually be something going on that is switching it that I don't know about. I don't spend a lot of time thinking about nitrile C13 chemistry or NMR spectroscopy, and if you had them switched, I would certainly allow that to be correct. Okay, of the remaining three, I'm guessing, I think that carbon B right here, the one that's closer to the OH group, would have a higher shift value. The carbon I've labeled C would probably have a higher shift value than D, and I think what's going on here is what we saw before, that the carbons that are adjacent to nitriles actually end up being lower shift values than we normally expect. In the past, we've not seen anything below the magic number 20 unless it was a methyl group, and now we're finding that this nitrile is able to push associated methylene carbons or CH2 groups down below 20. And so you think about this kind of a sacred territory of methyl groups is now being violated. So that seems like a reasonable approximation of my C13 NMR peaks. I'm not 100% confident that they're correct, but at least I've got them grouped together in generally the right regions. The purpose of this question was to get you to think about the chemistry and the C13 NMR spectroscopy of nitriles, and also to emphasize that nitriles, while they are carboxylic acid derivative, generally tend to produce peaks around 120 instead of 170, which has been the case for all of the other carboxylic acid derivatives. Finally, with the nitriles, whenever you have a carboxylic acid derivative, we expect it to undergo both acid and base catalyzed hydrolysis. So here is my nitrile in the presence of an acid catalyst that will turn it into a carboxylic acid. And then in the presence of a base catalyst, it'll turn it into a carboxylate. In order to get to the carboxylic acid, as with all of the base catalyzed hydrolysis of carboxylic acid derivatives, we'd have to do a slight acidic workup here to turn that carboxylate into a carboxylic acid. The mechanism for these reactions is not quite a SNAC mechanism. And the reason for this is SNAC refers to nucleophilic acyl substitution, and this is not an acyl group. And so the reaction then starts to look a little different. But what you need to continue to do is bring oxygens into the carbon of the nitrile and continue to put hydrogens on the nitrogen of the nitrile. That's kind of the general trend. So here, under base conditions, we're going to plug the hydroxide directly into the carbon. We end up with a nitrogen with a negative charge. I made a point before that even under base conditions, you don't expect a nitrogen to carry a negative charge. And that was true for sp3 hybridized nitrogens. When you have sp2 hybridized nitrogens like this one, they're actually a bit more electronegative, and I'm a little bit more comfortable putting a negative charge on a nitrogen that's sp2 hybridized. So under base conditions, I'm actually going to go ahead and allow this particular nitrogen to carry a negative charge. Then this negatively charged nitrogen is going to pull a hydrogen off of water. Even under base, you're definitely going to have water present. We'll get that water right back here in the next step when the hydroxide pulls a hydrogen off to generate the carbonyl group. So we're constantly moving bonds from oxygen into the carbon and moving bonds from carbon out to the nitrogen and then putting hydrogens on the carbon. Again, we have a nitrogen with a negative charge. And again, I'm okay with that because this nitrogen with the negative charge can actually resonance delocalize that negative charge up into the oxygen. So it's not a full -1 charge on an sp3 hybridized nitrogen. This thing will pick a hydrogen off of the water. Now we're at an amide. And at this point, you should recognize the SNAC mechanism. Base catalyzed hydrolysis of an amide in the first step involves a nucleophilic attack. This is step 2 of the SNAC mechanism. Step 4 of the SNAC mechanism is where we pre-protonate the leaving group. Then we drop down in step 5 and get our carbonyl back, push off the leaving group, and end up with step 6 of the SNAC mechanism where we pluck off any acidic hydrogens. So yes, this is a very long mechanism, even for a base catalyzed reactions, but the steps that are new to us here are the conversion of the nitrile to the amide. Once you get to the amide, you continue to hydrolyze this under base conditions until you get to the carboxylate. You might ask, could we stop at the amide and just carry your nitrile to an amide? And the answer is, I think so. I'm not certain, but the reason I think so is because the amide is more stable and less reactive than the nitrile. And if you have a chemical reaction where you can produce an isolatable intermediate that is more stable, it's going to stall out there. It'll hang out there for a while and won't react as quickly. So I imagine that if you're careful, you could probably get this to hydrolyze to the amide, but most of the time we're going to carry them all the way through to the carboxylate. The acid catalyzed version of this mechanism is very similar to the base catalyzed until you get to the amide, and then it's identical to the amide hydrolysis that we saw in the previous lecture. And that mechanism I'm going to push over to the homework and let you try to figure that one out. One more chemical reaction that we look at that's not really related to SNAC or hydrolysis, or kind of it's its own thing, is the reaction of a Grignard with a nitrile. And when you react a Grignard with a nitrile, you get to an imine. Imines are the carbonyl version, but when you have a nitrogen, and then we can hydrolyze the imine to a ketone. The power of this chemical reaction is that it allows us to convert nitriles to ketones. And one part of the ketone comes from the original nitrile. The other part of the ketone comes from a Grignard that we add to the chemical reaction. Mechanistically, this reaction, I only have half of that, don't I? So we don't have a mechanism right here for the first reaction. So let's go ahead and show that because it's a relatively straightforward two-step mechanism. So this organolithium compound, and rather than show it as a methyl group, I'm just going to be generic and refer to it as an R group right here, combined with a Grignard or an organolithium compound. The carbon that represents this R group right here carries a significant negative charge. So when we take these electrons away from the magnesium and plug them into the carbon of the nitrile and push those electrons out onto the nitrogen, we have changed a significant negative charge on a carbon to a significant negative charge on a nitrogen. And under basic conditions that can handle a negatively charged carbon, they can definitely handle a negatively charged nitrogen. So at the end of this step right here, let me refer to this as R1 so that we differentiate that one of the R groups came from the original nitrile and the other R group comes from my Grignard. I end up with my pre-imine. So notice that to get from here to here, the actual imine, what I need is a hydrogen. And that's why we do a water workup in the second step. You don't need to do an acidic workup here because nitrogen is such a strong base that it can rip a hydrogen off of water. When you pull that hydrogen off of water, you're trading a nitrogen with a negative charge for a hydroxide, which is an oxygen with a negative charge. That's a significantly weaker base, and equilibrium would favor the formation of that weaker base. That takes us to the imine. So these two steps get us to the imine. And then the next slide is going to show how we get from the imine here to the ketone. Now, before we start walking through this mechanism, I would encourage you to count the number of steps. 1, 2, 3, 4, 5, 6. And guess what? This is a SNAC mechanism. This isn't an acyl group, but we're definitely conducting a substitution reaction, where this nitrogen is being substituted off in place of an oxygen. This is done this is an acid hydrolysis of an imine to form a ketone. And so under acidic conditions, which is specified by the reaction, we pre-protonate. In the SNAC mechanism, this would be the carbonyl oxygen. Here it's a nitrogen. So step 1 is protonation of the nitrogen. Step 2 is nucleophilic attack. This is hydrolysis, so the nucleophile is water, to break the carbon-nitrogen pi bond. Step 3, we deprotonate the nucleophile that we just brought in. Step 4 is we're going to pre-protonate the leaving group. Step 5 is where the oxygen's electron pair drops down and ejects the leaving group. and step 6 is cleaning up any acidic hydrogens on the compound. So this is a snack mechanism in disguise because it's got a carbon-nitrogen double bond instead of the carbonyl group that we typically see with the snack mechanisms. Is the acid catalytic or stoichiometric? Well, let's take a look. So here the acid is being used. Here the acid is being regenerated. Here the acid is being used. Here the acid is regenerated. So catalytic means that you get it back by the end of the chemical reaction. What becomes of the NH3 that we push off in this reaction? Oh, the NH3 is a weak base, but a base nonetheless, and under acidic conditions, this NH3 would not last a hot minute. It would pick up a hydrogen right away from solution and become NH4+, which is called ammonium. None of that is organic, so we don't care. But evidently that question was important to me when I built this slide some number of years ago. So let's look at the summary of what we've looked at in this lecture. We talked about the stability of nitriles, that they are the most stable and least reactive of the carboxylic acid derivatives. They also have the lowest priority of any of the carboxylic acid derivatives when it comes to nomenclature. For spectroscopy, we talked about how in the C13 NMR there is that unique peak at 120 that corresponds to the carbon in the nitrile, and this is different from all the other carboxylic acids where the carbon of those carboxylic acids derivatives was showing up at 170. The IR makes that strong peak at 220, and in the mass spec we see a significant M-1 peak. We looked at different reactions for making nitriles. This is from chapter 7. It was from the first half of organic chemistry, where we took nucleophiles and knocked off halides to produce nitriles. I'm going to get to that. Evidently this is chapter 8, and it might be true. The book changed chapters recently, and I haven't gone through and updated all of my notes. A previous chapter, let's put it that way. We also looked at how you can make nitriles by reacting ketones and aldehydes with cyanide to produce the cyanohydrins. And then we looked at the dehydration of amides to make nitriles, and this was a mechanism using POCl3 that we looked at today in this lecture. Then we looked at 3 different ways of breaking nitriles. 1 and 2 are hydrolysis under either acid or base conditions. So when I said 3 ways of breaking nitriles, I'm counting acid hydrolysis as one and base hydrolysis as the other. We walked through the base hydrolysis of nitriles to make carboxylic acids. In this lecture, you're going to look at the acid catalyzed version of that in the homework, and it's a bit longer. Finally, we looked at the conversion of nitriles using a Grignard to make the imine, and then the hydrolysis of the imine to make a ketone or aldehyde using the snack mechanism. So a few mechanisms to look at today, as well as some new details to think about with your spectroscopy. Hopefully the homework gives you sufficient experience when you're practicing these problems.